Hello, this is the second video of DSC and ADC architectures. So in the previous video we discussed the different DSC architectures such as resistor string DSC, R2R DSC, current steering DSC and charge scaling DSC. Okay, so now we discuss the another DSC structure, that is cyclic DSC. Okay, cyclic DSC uses some of the cycle DSC uses simple components, a couple of simple components to perform conversion from digital to analog. Okay, the conversion by cyclic DSC is shown with the help of the block diagram of cyclic DSC. So this block diagram consists of a parallel to serial converter and switches. Then there is a summer and a sample and hold circuit. Then there is an amplifier with a gain 1/2. So here the conversion is in cyclic DSC. The conversion is takes place in serial manner. That is, the conversion is takes place bit by bit. So for example, if it is an n-bit DSC, that take n bit time for the conversion. For example, it is a 3-bit DSC, that take 3 times for the conversion. For each bit it take a conversion time. Okay, that is the cyclic DSC. So here the input data, that is the parallel input data, that is dn-1 to d0 is converted into serial by parallel to serial converter. So one bit is converted at one time, at a time. Okay, the next bit is converted in the next time. That is cyclic DSC. So parallel to serial converter convert the parallel digital input into serial, then that is given to the switches. So one switch is connected to VREF and another switch is connected to ground. So depending on the type of the serial input, the switch is either closed or open. If the coming input is 0, what about the decay bar is on and decay is 0? Okay, so decay bar is on means it is connected to ground. So input is 0, that is connected to our summer. Okay, then what is the function of the summer? That summer add the input signal with a output feedback signal. The output feedback signal is obtained with the help of sample and hold circuit and amplifier. Okay, so the summer adds V reference or ground to the feedback signal depending on the input bits. Okay, an amplifier with a gain of 1/2 feeds the output voltage back to the summer. Okay, such that output at the end of the each cycle depend on the value of output during cycle before. Okay, here every input is added with a feedback signal. That feedback signal is obtained from the previous cycle. Okay, previous cycle. So the input bit is treated in a serial fashion, that is added with the summer with a feedback signal. That feedback signal is obtained from the previous cycle. Okay, that is the conversion process of cyclic DSC. So finally the Vout is obtained by the equation Vout of n is equal to dn-1 into Vref plus 1/2 VAn-1 all into by 1/2. Okay, so VAn-1 is the feedback signal. Okay, so this is the output of analog output of a cyclic DSC. And here always assume that initially the output of a sample and hold circuit is always 0. Okay, and the accuracy of this converter is depends on some of the factors. one factor is gain of the amplifier needs to be highly accurate, and that amplifier is usually generated with passive capacitors. Then summer and sample and hold circuit need to be accurate. Okay. So okay, this is the explanation of that cyclic DSC. Then consider an example for the working of this cyclic DSC. So the input bit is 110101, that is D5, D4, D3, D2, D1, D0 is 110101. So we want to convert that digital into corresponding analog. Assume V reference is equal to 5 volt. So how many number of cycles will take this cyclic DAC for the conversion? Here 5 bits. So 5 cycles plus 1. 5 cycles plus 1. That is the difference. 6 cycles to produce analog output voltage. Okay. So in the case of cycle number 1, n is equal to 1. So what is dn minus 1? Here n is 1. So 1 minus 1 is 0. So that is d0. So what is the value of d0? Its value is 1. Then what about Vn minus 1? Initially sample and hold circuit output is 0. So Vn minus 1 is 0. So what about Vout? According to our equation, 1 by 2 into dn minus 1 is 1. So 1 into Vref. Okay. That is 1 into 5. Plus Vn minus 1 is 0. So 1 by 2 into 5, that is equal to 2.5 volt. Then cycle number 2, what is the value of dn minus 1? 2 minus 1 is d1. d1 is 0. Then what about Vn minus 1? That Vn minus 1 is the feedback signal of the previous signal. Okay, previous output. That previous output is divided by 2 by that amplifier. So initially the previous output is double the value, double the output. Okay. So here this Vn minus 1 is 5 volt. 2.5 double, it's a 5 volt. So 0.5. So finally Vout is equal to 1.25 volt. Then again for 3, dn minus 1 is 1. Then 1.25 double is 2.5. So that is equal to 3.125. Okay. 3.125. Okay. Then 6.25. Then what about 3.125, 6.5625? So finally after 6th clock cycle we get the analog value 4.14. So the feedback signal is previous value. So here also 2.5. So its value is 2.5. That is, this Vout is half into Vn minus 1. That is the Vout always. So we take this 2.5, this 1.25, 3.12. We can also directly write here it's a double value. Okay. So finally we get 4.14. So this is about cyclic DSC. Then next DSC is the pipeline DSC. So the pipeline DSC, in the case of cyclic DSC, n clock cycles are required for n-bit conversion. Okay, n-bit conversion, that is here this is how many bits? 2 for 6 bits. Okay, so 6 clock cycles are required for the conversion in the case of cyclic DSC. So if we come to pipeline DSC, instead of recycling the output back to the input each time, we extend the cyclic converter to n stage. In the case of cyclic converter, we always feedback the output to input. Okay, in each time. But here instead of using that feedback signal, we extend the cyclic converter into n stages. Okay, where each stage perform 1-bit conversion. Okay, this extension of the cyclic converter is known as pipeline DSC. That is shown in the figure. So here consists of n stages, stage 1, stage 2 up to stage n. Each stage consists of a switches, sample and hold circuit and a amplifier. Okay, so instead of feedbacking, here we extend the cycle converter into n stages. Okay, here the signal is passed down the pipeline, that is each stage work on one conversion. The previous stage can begin processing another, that is if one stage perform conversion, the previous stage is processing that one. Okay, so at a time all the stages are working. Okay, so therefore an initial n clock cycle delay is experienced as the signal at the first time. After that n clock cycle delay, a conversion takes place at every clock cycle. There is a first clock cycle for the conversion, for the conversion of first bit. So after that each stage perform conversion. So after the n clock cycle delay, the conversion will take place in every clock cycle in the case of pipeline DAC. Okay, this architecture is very fast as compared to cyclic DAC. Then the trade-off is, in the case of pipeline DAC we use more stages, so the number of components will increases. So the circuitry take more area. Okay, so it take more area but its speed is high. So the output is also here written as the same output, that is each stage output is dn minus 1 into Vref plus Vout n minus 1 into 1 by 2. Okay, so the output is written as in the pipeline DAC, the output is written as dn minus 1 into Vref plus Vout n minus 1 into 1 by 2, slightly different from the cyclic DAC. Okay, so the operation of each stage in the pipeline can be summarized as, if the input bit is 1, add Vref to the output of the previous stage divided by 2 and pass the value to the next stage. If input is 0, simply divide the output of the previous stage by 2 and pass along the resulting value. Okay, that is if input is 1, add Vref. If input is 1, add Vref, that is dn minus 1 into Vref plus Vout n minus 1 into 1 by 2. The explanation of that mathematical equation is, if the input bit is 1, that add with Vref to the output of the previous stage, divide by 2, that is dn minus 1 into Vref, that is 1 into Vref plus Vout n minus 1 into 1 by 2. If the input bit is 0, simply divide the output of the previous stage by 2 and pass along the resulting value, that is dn minus 1 into Vref is 0. Okay, then this pipeline DAC working is also explained with one example. Okay, this is an example shown in the textbook. So here we want to design a 3-bit pipeline DAC in order to convert the digital inputs 0, 0, 1, 0, 0, 1 and 1, 1, 0 and 1, 0, 1. Okay, so in the pipeline DAC, the first stage always convert the LSB, second stage convert the middle digit, third stage convert MSB bit. That is the process of conversion. First stage convert the LSB, second stage convert the middle digit and third stage convert the MSB. Okay, and similarly once the LSB of the first word is performed and passed on, the LSB of the second word begin its conversion. Okay, that is here there are 3 words. So first the LSB of the first word is converted. After that the LSB of the second word begin its conversion. Okay, similarly once the LSB of the second stage is completed and passed on, the LSB of the third word can begin. Okay, So for example, the first clock cycle, here the input data is 001. 001 is, here the LSB is 1. Okay. So when a digit is 1, what happens? That is 1 into Vref, that is 5, plus Van minus 1 is 0, divide by 2. That's 5 divided by 2, that is 2.5 volt. Then Vout 2 0, Vout 3 0. Okay. Then clock cycle 2. Clock cycle 2, that is in the clock cycle 2, Vout 1 is the LSB of the second word. LSB of the second word, what is the LSB of second word? Second word LSB is 0. So its value is 0 means, what is the output? 0. Okay, that is D 0, then feedback is also 0. Okay, here there is no feedback. So Vn minus 1 is 0, Vout n minus 1 is 0. Then third clock cycle LSB conversion Vout to 1. So again its value LSB is 1, so its value is 2.5. Then in the second clock cycle, what is Vout 2? Vout 2 is the output of the middle digit of first input word. First input word. So the first input word, the middle data, that is 1.25. Okay. Then Vout 3, that is 0.625. Okay. Similarly, in the case of second clock cycle, here it is 0, then 2.5, that is in the third clock cycle, that is the middle data of the second word. Then 3.75 is the MSB of the second word. Okay. Again this third clock cycle 2.5, 2.5 is the LSB of the third word, 1.25 is the middle word of the third word, and 3.125 is the MSB of the third word. Okay, that is in the first clock cycle all the LSBs of all three input words are converted. In the second stage, convert the MSBs. Okay, third stage second stage convert the middle digit, and third stage convert the MSB. Okay, so during the first clock cycle, it perform only the first input word LSB conversion. Okay, in second clock cycle, it perform the LSB of second word and middle word of the first word. In third clock cycle, it convert the LSB of the third word and middle word of the second word and MSB of the first word. Okay, in the fourth clock cycle, it convert the middle word of the third word and MSB of the second word. Fifth clock cycle, it convert the MSB of the third word. So it takes only 5 clock cycles to convert 3 input words. But in the case of cyclic DAC, for the conversion of each input word, it take n times. Okay, that is the difference. Okay, so we come to, so these are about DAC architectures. So next we come to ADC architecture. So ADC architecture, first we discuss ADC means analog to digital converter. Okay, so here also different types of ADC structures are available. So first we discuss the first ADC structure, that is flash ADC, flash type ADC. Okay, so flash type ADC. So do you heard about flash type ADC? We already studied this flash type ADC in our BTech syllabus. Okay, so flash type ADC means it is also known as parallel converter. It is the highest speed ADC. And this flash ADC mainly consists of comparators, resistors and decoders. So how many comparators are present? If it is an n-bit ADC, it consists of 2 raised to n minus 1 comparator and 2 raised to n resistors. And in order to convert the output of the comparator into digital, we use decoders. 2 raised to n minus 1 to n decoders. Okay, so the output of the comparator is a thermometer gauge. Okay, that is here the resistors are connected to one of the input of the comparator, and the other input of the comparator is the reference voltage. Depending on the values between the voltage generated at each input of the comparator compared with the reference value, it produces either 0 or 1 at the output level. Okay, output level. So consider this example. So we want to generate a 3-bit flash ADC. So it is a 3-bit flash ADC. So 2 raised to n minus 1, 2 raised to 8 minus 1, 7 comparators are needed and 8 resistors are needed. So 7 comparators are represented C1 to C7. Resistors are all are equal values R, and one end of the resistor is connected to Vref and other end is connected to ground. Then other inputs, so that is connected to op amp. Then input is connected to op amp. Okay, so plus terminal of op amp comparator is connected to input bit. Okay, here ADC, analog to digital value. Then Vref. Okay, that is our Vref is connected to resistor. So according to the voltage divider rule, each resistor generate a potential at negative terminal of each comparator, that is represented as V7, V6, V5 up to V1. Okay, that voltage is generated by using the according to the voltage divider rule. We can write that is equal to VI is equal to V reference into I by 8. Okay, here it is a 3-bit ADC, so we can write it as Vi is equal to Vref into I by 8. Okay, for example, V7 is equal to Vref is equal taken as 5 into 7 by 8. Okay, that is V7. So that value is 4.375. For example, V1 is equal to 5 into 1 by 8. That value is equal to 0.625. That is 0.625. Then the next value is equal to 1.25. That is 5 into 2 by 8. Okay, then 5 into 3 by 8 is 1.875, 5 into 4 by 8 is 2.5. Similarly, we can find the different values at V1 to V7 values. Okay, then we want to compare. Okay, so if Vn is between ADC output, ADC is a staircase output, so Vn is between 0 to 0.65, between 0 to 0.65, what is the output? Output is 0 to 0.65, 0.625. Its value is 0. Okay, so the output of the comparator, all output of the comparator is 0. Okay, when Vn is between 0.625 and 1.25, the first output C1 comparator output is 1, all other comparator output is 0. Similarly, Vn is 1.25 to 1.875, the second comparator output and first comparator output C1, C2 is 1, all others are 0. Similarly, we can write this combination, that is our thermometer code. Okay, the corresponding digital data using the decoder is, the first one is 0, second is 1, this is 2, etc. So we can convert the analog value into digital. That is shown in the diagram and also represented in the table. So advantage of this converter is high speed. Okay. Then the drawback is number of comparator increases. If number of bit increases, comparator is also increases. That is the main drawback. So number of comparator increases means area and power requirement is also increases. Okay, that is the main drawback of flash ADC. Okay. So these are the equations of DNL and INL for flash ADC. So study the final equation for DNL and INL. Okay. Then next we discuss the next type of ADC, that is two-step flash ADC. This is another type of flash converter. That is, it is the another type of parallel converter that is known as two-step flash ADC. It consists of two steps. In the first flash ADC, it's only a one step. Here this consists of two steps. Okay. So this converter is separated into two complete flash ADC with a feed forward circuitry. This consists of two complete flash ADC with a feed forward circuitry. Okay. The first ADC generate a rough estimate of the input value and second converter perform the fine conversion. Okay, the advantage of this two-step flash ADC is we can reduce the number of comparator. Okay, in the flash converter, the number of comparator for a n-bit ADC, number of comparator is 2 raised to n minus 1. If we come to two-stage flash ADC, the number of comparator required for a n-bit ADC is 2 into 2 raised to n by 2 minus 1. For example, 8-bit flash converter requires 255 comparators, while in the case of two-step flash requires only 30. So that is the advantage of this two-step flash ADC. This consists of two complete stages of flash ADC, one for rough estimation and another for fine conversion. Okay. So how it's converged? The conversion process is after the input is sampled. Okay, the MSBs are converted by the first flash ADC. MSB are converted by first flash ADC. This result is, that is the diagram. Consider this diagram. Okay, so the input is sample and hold, and that is given to MSB ADC. This is the first ADC. This convert the MSB into corresponding digital data. Okay, that digital data is given to a DAC. That DAC convert the corresponding analog signal and it is given to a subtractor. Okay, so what is the function of this subtractor? Okay, the subtraction is, that is, the result of the subtraction is known as residue. Okay, then it is multiplied by 2 raised to n by 2 and input into the second ADC. Okay, the second ADC produces the LSB through flash conversion. That is, the first ADC MSB conversion, that is given to a DAC. The DAC produces corresponding analog voltage, that is given to a subtractor, that is subtracted and it is multiplied, that is output of the subtractor is known as residue. It is amplified by a 2 raised to n by 2. Then it is given to a LSB ADC that convert the corresponding digital data. Okay, so two stages, one stage for MSB conversion and another stage for LSB conversion, and first stage is for rough estimation, second stage is for fine conversion. Okay, the first conversion is known as coarse conversion of MSB. Second stage is the fine conversion. So coarse conversion and fine conversion. Okay, so this is about two-stage flash ADC. The main advantage is we can reduce the number of comparators as compared to flash ADC. Next we discuss pipeline ADC. Pipeline ADC. Okay, so same as that of DSC, pipeline DSC, here consists of n stages. N stages. That is, this pipeline ADC also is an n-step converter. That is, each bit is converted by each stage. Okay, so this is high resolution ADC and fast. So this pipeline ADC consists of n stages connected in series. N stages connected in series. So first stage MSB, then Dn minus 2 stages, Dn minus 3 stages, then D0 stages. N stages in series. Each stage consists of a 1-bit DAC. Each stage consists of a 1-bit ADC. ADC means that is our comparator. A sample and hold circuit and a summer and a gain 2 amplifier. Each stage consists of a sample and hold circuit, a 1-bit ADC that is our comparator, and a summer and a gain 2 amplifier. Okay, so what is the function of each stage? How it conversion takes place? Okay, so the input, this is our input, that is sampled by the sample and hold circuit. That the output of the sample and hold circuit is VP1, that is given to the ADC plus. Then the ADC minus is connected to a voltage, that is V reference by 2. So this comparator or ADC compare the input voltage with V reference by 2. Okay, if Vn is greater than V reference by 2, the output of the ADC or output of the comparator is 1. Okay, output is 1. And if Vp1 is less than V reference by 2, Vn is less than V reference by 2, the output of the comparator is 0. If output of the comparator is 1, that is Vn is greater than Vref by 2, that control the input to the summer. Okay, so if output of the comparator is 1, the subtracted, that is that Vn is subtracted from the, that is Vref by 2 is subtracted from the held signal and pass the result to the amplifier. Okay, if Vn is less than Vref by 2, pass the original input signal to the amplifier. Okay, so the output of the each stage in the converter is known as residue. Okay. Okay, so the output of each stage is passed to the next stage. Okay, so this is about pipeline ADC. This is the working of pipeline ADC. Okay, so the remaining ADC structures are explained in the next video. Thank you.